Thank you. I'll begin. Begin with a word of prayer. So, Heavenly Father, we thank you for this day, and I just pray again that you bless this class, help us to understand a little bit more about integration, and just help us to prepare for the test, which is upcoming. Lord, in your name I pray. Amen. So, you guys have any particular questions? Before that though, just for the sake of continuity of discussion, I should make me misbehave a couple more minutes. If we have f of t, which is u as a function of t plus I times v as a function of t, so like for example, e to the it is cosine t plus I times the sine of t, then in this case we say that the real part of f is u, we say that the imaginary part of f is v. So like this imaginary exponential, this is the real part of the imaginary exponential, this is the imaginary part of the imaginary exponential. Sine and cosine both in there. So just so you know, definition, if I want to differentiate such a thing, it's really, really complicated. So hold on. The way you differentiate a complex valued function of a real variable is you differentiate the real part, and then you differentiate the imaginary part, and you do it separately, and you add it, and that's it. So this is how we differentiate. So here, set theory, f is a function that takes a real input and gives a complex output. So that kind of function, the calculus of it it's pretty easy. It's just like the calculus you already know, but you do it for the real part and the imaginary part separately. In similar way, the integral of f dt, guess what? It's the integral of u dt plus I times the integral of v dt, where those are garden variety ordinary integrals, and we can make them definite if you wanted. And so the fundamental identity, and I won't work this out because we got other stuff to do today, but you can prove, I did it in differential equations like this last Thursday. It took me about 10 minutes of calculation. It's not that hard, but it's not that easy. But the derivative with respect to time of e to the alpha plus I times beta t, all right, is equal to, so what would this be? This is the derivative with respect to time. The way this works is that's e to the alpha t, e to the I beta t. What's e to the I beta t? Cosine beta t plus I sine beta t, yeah? Talked about this a little bit in here. And so that's d dt of e to the alpha t, cosine beta t plus I d dt e to the alpha t sine beta t by the definition I just stated. And how do you differentiate product of exponential and cosine and a product of exponential and sine? You do what? Product rule. There's chain rules all over the place, right? You got alphas and betas flying here this way and that way. And after a little bit, you get this. Alpha plus I beta e to the I times alpha plus I beta t. In other words, we have the following simple identity, which is the derivative with respect to time of e to a complex lambda times time. It's just lambda e to the lambda t. So corollary, if I integrate e to the lambda t dt, that's just going to be 1 over lambda e to the lambda t plus a constant. So it turns out that formula that you learned in Calculus 1, it continues to be true even when lambda is a complex constant. And I showed you at the end of the last class how that allows you to calculate certain integrals here in novel ways, better ways really. But it comes at the cost of learning some complex variables, right? Which you may or may not be comfortable with at the moment. So let me do the example I did at the end of last class with integration by parts now. So, and then I'll take your homework questions, okay guys? So example 1, if I integrate e to, let's say, 2x what was it? What did I'm sorry, guys. What did I integrate at the end of last class? I can't remember. What was it exactly?
E to the 3 plus I.
Okay, so it was e to the 3x cosine of x was something I found the integral of, right? And I also found the integral of sine.
Yeah, just use t instead of x.
Oh, I used t. We can do a t. Let's do t. Let's do t. All right. So how do we do this? If you don't know the sneaky complex variables trick I showed you last time, how do you do this? Integrate by parts, right? So pick your poison. I'll make this dv. I'll make that u, mostly because I wrote that first and that second. You could go the other way, it'd be fine. But so I have e to the 3t, and then sine of t, right? Because if v is equal to cosine t dt, I mean if dv is that, then that's v, right? We agree? Okay. Then minus the integral of sine t, right? That's my v, and then du is 3 e to the 3t dt. Okay? So that gives me e to the 3t sine t minus 3 times, and I'll do parentheses, the integral of e to the 3t sine of t dt.
Isn't 3 times e to the 2t because we have to take our du?
But if u is e to the 3t, then du dt of course is 3 e to the 3t, right?
Sorry. Yes. Never mind. I was confusing concepts.
That's.
Oh, never mind.
I pulled it out. It's cramping my style. So now I will integrate by parts again, because integrating by parts is so much fun that we can't help but do it again. Let's see here. Take a drug. I mean, drugs are bad. It's like Dancing with the Stars. It's just, something we approve of. Let's see here. See here, U1. Sorry, I digress. I'm working on editing this video. I better shut up. All right, so U1, dV1. Does that work? I mean, that's something we can do, right? So this will be, get to the point here, e to the 3t sine t minus 3, parentheses are your friend. And let's see here. We get what? What's V1? Right, negative cosine, so I'll bring that minus out. Minus cosine, and then I get plus integral of cosine t, right, times, again, 3 e to the 3t dt. Minus minus give me a plus, because I get a minus from the integration by parts, but I also have a minus from the integral of dv, right, dv1 rather. I guess I should make those two, sorry, it's bothering me. This would be u2 and dv2, and this would be u1 and dv1. As you can see, they're not the same, right? All right, so let's clean things up. Almost done, almost home. So this is e to the 3t sine t plus 3 e to the 3t cosine t, right? Minus 9 times the integral of e to the 3t cosine t dt. I don't think you need to write this, what I'm about to write, but I'm writing it because if I don't, you guys are going to ask about it. So I is equal to, this is I, equal to e to the 3t sine t plus 3 e to the 3t cosine t, right, minus 9i. This is I. So we add 9i to both sides, right? And we solve for I. So the integral of e to the 3t cosine t dt is 1/10 e to the 3t sine t minus 3/10 e to the 3t cosine t plus a constant. I know I should add a constant because we're calculating an indefinite integral, and we should always allow for an arbitrary constant to express that we're finding the indefinite integral. Yeah.
Do you have to put everything in parentheses because we're 1/10?
I distributed the 10th.
Okay. Okay.
You could also use parentheses with the 1/10 out front. You could also pull e to the 3t out if you wanted. Yeah.
Why do you go from adding the two terms to subtract? If it's just dividing the whole thing?
That's a good question. I think it's because I wasn't done writing yet. There you go. No, that was a mistake. Sorry. Of course, I did that on purpose to see if you're paying attention. Just kidding. I guess I could blame women. Fallen man, right? I mean, why do we live in a fallen world? Who was it? You guys remember? Have you ever heard like the ultimate sexist sermon where it's the hypothesis is put forward that Adam knew he shouldn't partake in the fruit, but he did so that he could keep Eve company? You guys ever heard this? It's like it's even worse than what I said, right? It's just because Adam was loving and he didn't want to leave her alone in death. It's like I'm pretty sure that's a wrong interpretation of what happened, but I think everyone involved was at fault except for God. But anyway. Let's see here. Genesis aside, any questions? No? So you can appreciate what I did at the end of last class, yeah? I don't know. I think it's kind of neat. We pick up integrals like this in the same way we do calculus 1 integrals. We just have to do a little algebra, right? It's not entirely for free. You have to learn how to do things like this, right? If I have 1 over 7 plus 2i, how do I put it in Cartesian form? I do 7 minus 2i, right? Over 7 minus 2i times 7 plus 2i. This is how we put a complex number, a reciprocal complex number, into Cartesian form. We multiply by the conjugate over the conjugate. Basically, that was the non-obvious trick that I had to use to bring the I out of the denominator up into the numerator in order to pick off imaginary and real parts. Okay, let me shut up. So, are there other questions about homework? Yeah. Mm-hmm.
So it's 8.4.
8.4, number 30. Ooh, this one looks like fun. So we're supposed to integrate x squared plus 5 to the 3/2 in the denominator, right? Well, 5/2, right?
No, it's 3.
Oh, it was 3?
Wait. Yeah, it was 3/2.
Oh. 3/5. No. You don't want that. that would not be good. So we make a x equals to square root of 5 tangent theta substitution. Then this, with that trig substitution, we get root 5 secant squared theta d theta divided by, so this means that x squared plus 5 is going to be, square root of 5 tangent theta squared plus 5, also known as 5 times tangent squared theta plus 1, aka 5 secant squared theta. Usual song and dance. So this is 5 secant squared theta, but don't forget the 3/2 power, right? So laws of exponents, we have, we've got a root 5. I'll bring the constants out front. Root 5, and we also have a 5 to the 3/2, right? And then we're looking at the integral of, I could simplify it. I'm just, that's what, secant. Hey, this is nice. Ooh, this is really nice. I wish I'd done this one the other day. So secant squared to the 3/2 is secant cubed. But I got secant squared upstairs. So I got the integral of 1 over secant. Which kind of sounds bad because secant's really complicated, right? So like 1 over the integral of something that's really complicated seems like it should be bad. But this is not bad, because 1 over secant is cosine, right? And this is so I'm looking at root 5. This guy is actually 5 root 5 integral of cosine theta d theta. So what we got 1/5 sine theta plus a constant. Oh, this problem, this is beautiful problem. I really like this problem, really nice. This is everything I wanted to illustrate the other day, and none of which happened for me. Let's see, so tangent theta is equal to x over the square root of 5. Right, so I can draw my triangle. Got my theta, opposite, adjacent. The hypotenuse is what? This should not be surprising at this point. X squared plus 5, right? Yeah. X squared plus the square root of 5 squared, also known as 5, yes.
Is it always going to be like that?
So far as we've seen, that's what happens, yeah. Always is a really powerful word, but you know, the examples that we come across in calculus 2, this seems to happen, yeah.
If we assume it's always like that, it will be.
I want to believe that if I deliberately tried to construct an example to make your statement false, I could do it. But I don't know that example at the moment, so short of me being a jerk, I think, yes, it's always going to be the case. Don't worry, I don't have enough time to construct such an example this semester, so you're safe. So this is 1/5. What's sine theta?
X over squared, x squared.
Very good. And there you have it. So let me just take a second here to make a couple of sort of big picture comments, yeah? So if we have something that looks like x minus, say, alpha squared plus beta squared, right? And if we, well, I guess I don't really want to go, I mean, I could put a, I could try to go and make it even more awful, right? What happens if you put like an m over here? What kind of substitution should you make to take care of an expression like that? See, what I would do is I would make a, let's see here. Basically, I would want this to function like beta squared tangent squared theta, right? That's kind of what I want. Because then I'll have beta squared tangent squared plus theta, and that'll allow me to extract a secant squared theta from that. So with that in mind, that suggests to me that the substitution I want would be, x minus alpha equal to what? It looks like beta tangent over the square root of m. See, because if I do that, then this becomes that, right? And so with that substitution, this whole thing just becomes beta squared secant squared theta. For example, if I was going to try to integrate the square root of 2 times x minus 3 squared plus 17, which is pretty awful, then I'm pretty sure if we make a x minus 3 equal to square root of 17 tangent theta divided by the square root of 2 substitution, that will serve us well. Because then square root of 2 times x minus 3, that squared, right? That's going to be 2 times x minus 3 squared, but what else is it going to be? It's also going to be, oh, maybe I did this wrong. No. Oh, no. I'm sorry. Sometimes you have to admit your limitations. I'm going to get rid of that m for now. If you guys were the first class I taught, I'd try for the m. But I'm going to dial it back a bit here. So this clearly indicates a substitution of beta tangent theta. And on the other hand, if we had something like x minus alpha squared minus beta squared, what substitution would we make? Sine? Because then I'd have sine squared minus 1, which would be minus cosine squared. Then square root of minus cosine squared is in trouble. Secant, yeah. If we have, so the pattern is if we've got beta squared minus x minus alpha squared, then this one is what you just said, sine. It's a good substitution. What would the corresponding hyperbolic substitutions be if we were to make if we were to go to hyperbolic path instead? Remember, it always goes back to cos squared theta minus sinh squared theta is 1, right? So if this gives me what? This gives me cos squared theta minus 1 equals to sinh squared theta, right? And it also gives me that the hyperbolic tangent squared theta minus the hyperbolic secant squared theta is equal to 1. That's not particularly useful, but we can see that 1 plus hyperbolic secant squared theta is equal to hyperbolic tangent squared theta. Let's see here. So, getting to the point eventually. This one up here, let's see here. So this close cousin to this would be what? Cos squared theta is what? 1 plus sinh squared theta, right? So that reminds me of the secant squared is equal to 1 plus tangent squared, right? The same pattern as secant squared theta is 1 plus tangent squared theta. So that's the one that goes with here. I do x minus alpha beta hyperbolic sine. This one, I do hyperbolic cosine. I want to do hyperbolic substitution. And this one, let's see here. I've got number minus variable squared, right? Which one's that going to be? Is it tanh? Oh, you're right. So this one down here, tan squared minus 1 is secant squared, right? That one. That suggests if I make x minus alpha equal to beta hyperbolic tangent, then that'll be helpful. So those are your three basic patterns. Now, I was trying to throw in a multiplier of the squared variable in, but, you know, that's, maybe it's too much. We can always isolate x anyway, right? You just do arithmetic. Show you know what I'm talking about, right? Maybe not. Here, how about this one? If I have the integral of dx over, you know, 10 minus 2 times x minus 3 squared, I can turn that, I can get that 2, and I can make it behave, right? I can pull 1/2 out, right? Like that. And then I can go back to one of my standard templates. If we get, so what would you guys prefer, hyperbolic or trigonometric for this one? Here, let me make this more fun. 3/2. Mwahaha. So we don't usually put parentheses like that. 2 to the 3/2, right? Because I just pulled it out of that. So do you guys want to do hyperbolic or trigonometric for this one? Trigonometric? All right. So what would that be then?
X subtract 3 equals sine theta.
I heard a square root of 5 sine theta? Right. Good. 5.
Yes.
5, yeah. So if I do that, I have 1 over, I'd rather write that as 2 root 2. And this is the integral of dx, which is what? Root 5 cosine theta d theta divided by, and let's see here, what's 5 minus x minus 3 squared? It's 5 minus 5 sine squared theta, aka 5 cosine squared theta. So this is 5 cosine squared theta to the 3/2. And this one, see, it looks all friendly and stuff, right? Looks like it's your friend. It's cosine, right? But then what happens when we simplify? We got root 5 over 5 to the 3/2, right? This gives me what? Cosine theta over cosine cubed theta d theta, is that right? Oh, this isn't bad. This isn't bad. This is actually a very nice problem. Let's see here. So this is 1 over 2 root 2 times 1 over, well, that's the square root of 5 over 5 root 5, right? And then we're integrating what? We're integrating, looks like we're integrating secant squared theta d theta, which should not be a great burden to you, right? It's tangent, right? That should not require mental energy. So we got 1 over, looks like 1 over 10 square root of 2 tangent theta plus a constant. And then we can clean that up, right? Here's our triangle. Theta, we've got sine theta is x minus 3 over root 5. So what's the adjacent side? You know. What's that? It should be this thing, right? Square root of them. And so the answer is 1 over 10 root 2 times x minus 3 divided by the square root of 5 minus x minus 3 squared plus a constant. Yep.
During the test, do you want us to, I think you answered this before, but do you want us to convert it like how you do up there?
Yeah.
Yeah.
Yeah. Usually. I mean, sometimes you can't, right? But, you know, if I want to emphasize that, I might say something like, please leave your answer in terms of algebraic functions as much as possible. I usually try to throw that in there somewhere just to remind you guys that that's the, you know, that's the best answer. Now, if you wrote this, if you wrote your answer as 1 over 10 root 2 tangent of the inverse sine of x minus 3 over root 5, that wouldn't be wrong, right? So you get significant partial credit for that. It's just not the best answer. So depending on my mood, that either would be the case that you get full credit for that and a bonus point for this, or you might get full credit for this and like a very small deduction for that. I mean, it's not a big deal, but it's a deal. Why is it so hot in here? How many people are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We are missing 25% of the class. There's 20 people in here, I think, right? So, what's that? That's a good question. I think we had not a lot more. I think we had one in the first week who wasn't really there. He was like on my initial printed roster. He never came. He wasn't really a student in here. I feel like we might have had 25. I'd have to look.
How many people are usually left?
How many will remain? That's the question. Remember, Calculus 2, it's not a sprint. It's a marathon. Pace yourself. What's that?
I don't like Gordy.
Brando said that he had a Calc 2 class that started with like 17 and 4 people made it to the final.
Wow.
You know, I try not to mince words with you guys. I mean, Calculus 2 is a significant amount of work, and it's more work if you don't have like Calculus 1 settled, right? And I can tell from things I hear you guys say that there's still some sort of chinks in your armor from Calc 1, right? Now, it could be tiredness. It could be the heat in this room. So I don't know for sure. Only you know for yourself where you really are math-wise. But unless you're really lost, and then you just know that you're lost, right? You don't know how far it is to be found. I understand that. I've had that feeling in courses before. Not so much math courses, but you never know. Like, funny things can happen too, right? Like, I had this feeling like I was completely lost in this computer science course I took. Like, I did not. Like, 40, 50% of what this guy was saying, I was just like, I have no idea what he's saying. And the thing is, I had a 2-year degree in electronics before I took this course, right? So I had a class in assembly language, right? Where, I mean, we literally write out, you know, things about registries and like, you know, set flags and very, very base level computer stuff. And so I knew about that. I mean, so I had some background that should have helped me with the class, and that did help me understand some things he said. But I just had this feeling like, I do not know what's going on. So I took the first test, and I was just like, I'm going to drop this class. So I went to the professor to tell him, I think I'm going to drop your class. I don't really understand what's going on in here. And he's like, well, maybe you should look at your test before you drop. And I was like, okay. So I looked at my test, and I had a 99%. And I was like, what? Didn't make sense to me. And the thing was, there was some math in the course, right? And my math was so much better than like the computer science students that he always teaches. Because I could do things like fit a line between 2 points. Like, that's the math we're talking about. But to actually confidently know about fitting a line between 2 points during the course of lecture and saying things about it impressed him. Whoa, that's an indictment on computer science students. But anyway, so I was pleasantly surprised, and I was like, I guess I'll stay with the course. But I would not do programs in the course. So on my future test, he'd be like, you should have done this program. I'd be like, but I don't know how. So I don't know. There's another good thing about math. You can pass classes, I guess. But I did okay. But he was a very interesting professor. He's passed away a couple of years ago, but his last name was Funderlich. Funderlich. Isn't that an awesome last name? Oh, but that guy was a hoot. That was one of the weirder classes I took because I had got some very bad advising. Something many of you probably you've experienced this, no? How many people here feel like they've gotten bad advice from advising at some point here? I'm curious. Okay, so it's the majority viewpoint. See, I got advice from a physics professor that I should take numerical methods before I took some other course so that the other course would make more sense. And I understand, she's just having a conversation with this other professor who told her to do this, right? But it's crazy what she said. It's just not so cuckoo. And it did not help the other course. And then all my friends took this course in the physics department, and I couldn't hang out with them and have fun because I had taken this stupid course with Funderlich the year before. I'm still bitter about it. I never went back to that advisor for any advice ever again. That was the last time I listened to her. All right, I don't know if this really helps you with your calculus too, but I don't know, sometimes we have to take a break, I guess. Do you guys have questions? You must have questions.
Are we doing more homework?
Yeah, sure.
All right. Well, I have another question. Oh, no.
Mm-hmm.
How long have we done before? About 8.2 number 12?
8.2, number 12, you say? So let's see here. We're supposed to solve by the simplest method. Not all require integration by parts. Now, that is irrelevant because this is an integration by parts problem. So we got 5x over e to the 2x. We're supposed to integrate this thing, right? You said this was section 8.2, number 12? Okay, yeah, so let's look at that. So you guys excited about the math battle tomorrow? Excited? I'm thinking teams of 2. So there will be 10 teams. I have to go with teams of 2 because I've tried teams of 3 before and teams of 4. And what happens is that about a third of the class isn't really working on anything. And it's that third of the class that needs to be working more than the other 2/3. So I think teams of 2 is a good match for us because we only got 20 people, so that's 10 teams, which shouldn't be too bad. The question is, who do you want to be paired with, right? Yep. It's an in-class group exercise, but your group consists of 2 people. And as I said, it is a battle of math. Yep.
What is the prize of this battle?
That is yet to be determined. But I'm guessing candy.
And points.
Oh, it is worth points. That's true for everyone. I mean, yes, there is a token prize of points. Like you would like to earn 20 points. You would like to earn 20 points. You and your partner. You will turn in one assignment, both of you. One solution for the math battle. There's further instruction to be given tomorrow, but no. I think I've got like a dozen questions, some of which have subparts. So you probably want to like divide and conquer. You know, one person work one person the other. Try to work some in common so you can check each other. No. Okay, I'm sorry. Getting back to your problem. So this was the integral of 5x, and then the thing here that if you leave it like this, you're going to be like, I don't know what to do. What you got to do is this is e to the minus 2x. Okay. At which point it should start to be clear that we can make integration by parts of dv and u. I'm sure this is what Liotte would tell us, but I don't care. So this is uv minus integral of v du. And let's see here, u is 5x, so du 5 dx, dv, e to the minus 2x dx. So v is what? Negative 1/2 e to the minus 2x, right? And so here we go. This is minus 1/2 e to the minus 2x. I put the v first, if you don't mind. Oh, there's a 5 in the u. I'll pull that out here. 5/2, just for the sake of style. I'm sorry, just stylistically, I write this x e to the... It doesn't have to be written that way, but it's just, I feel like x should go before that just for stylistic reasons. And then plus 1/2, the integral of e to the minus 2x, what was du, times 5 dx, yeah? And then we can do that integral again. What do we get? Yeah, minus, there's a 5, right? So pull that 5 out. But yeah, the fourth is great. 4 e to the minus 2x plus a constant. And yeah, there you go. Wasn't that bad? It looks much worse than it is, yeah. If you don't make this step at the start and like that, then yeah. I don't think I know how to do it without that. Without that algebra, I don't think I could do it. I think that's true of most every integral I talk about in here. Without algebra, I can't do it, right? That seems like a safe statement. Yeah?
And you could have just pulled that 5 out again, right?
Sure, yeah. It kind of irks me that this example is given in the book, 5e to the 5x dx. He's like, this is e to the 5x plus a constant. You know, that's great. But what I'm noticing is that, well, at least I've seen at least one instance of this, is a student looks back at this, and somehow what they see is just this, right? But this example, really, we should do something like this. I mean, for future reference, it would have been more useful if the book had done this. Now, it was trying to make that example easier, which is a misguided goal. Yeah. I don't know. Of course, this is a u substitution, right? U equals 5x, so 5x dx is du. That's where the 1/5 is coming from. But partial fractions. You guys need to think more about partial fractions. Am I right? I'm right. I think so. So what if I had x cubed plus x divided by x minus 1 squared times x squared plus 4x plus 5 times x plus 1? What would the partial fractions decomposition be for this? We'll just set it up. We won't actually do the algebra this time, of course. So I got an a over x plus 1. Oh, you start, the first shall be last. I mean, last shall be first, I should say. So that's this one. Yeah, great. Very good. I say we're working Chinese style. I like it. B. Now you can either do, you can do bx plus c if you like, but what I've been encouraging you to do here would be something like b times x plus 2 plus c, and this is really, you know, x plus 2 squared plus 1, right? That's my point. That's completing the square here. And then, last but not least, d over x minus 1 plus e over x minus 1 squared. That would be the partial fractions decomposition for this. And then, of course, you have to work out a, b, c, d, e for an actual problem. If I don't want you to work it out, I will say something like set up, but do not find the constants of the partial fractions decomposition. And I usually the do not set up, I'll make like all caps and bold in the hope that you don't miss it, you know. But. All right. So we got about, what, 5 minutes left? 3. Just enough time for me to share another interesting but obscure calculus trick with you. Suppose you wanted to do something like integrate dx over, say, 2 plus cosine x. This is really tough, this problem. But there is a well-developed, in fact, general, somewhat general. So if you want, is that double-sided?
Yes.
Okay. I'll start you guys over here. Then you can pass it over and then back. And so this, what I'm showing you guys, is another trick. This is not something I expect you to, you know, I don't always test on this, and when I do, I usually give some kind of warning. But so the idea of this substitution is really beautiful, at least the algebraic side of it. If you let t equal to the tangent of x over 2, all right, which is like bizarre, right? Bizarre. Then this will tell you you can derive some things. For example, and I won't go through it because we're out of time pretty much, but you can work out that sine of x is 2t over 1 plus t squared. You can derive that the cosine of x is 1 minus t squared over 1 plus t squared. You can also derive that dx is 2 over 1 plus t squared dt. All right? So this, there's a derivation. It's about 5-10 minutes. Maybe less if you're completely confident about everything you're doing. You maybe can do it in less. But that's the case. So with those substitutions in hand, what happens when you come to an integral like this? Make this is called the Weierstrass substitution, which is, according to Wikipedia, a misnomer. Apparently this is due to Euler, which is not terribly surprising. But people typically call it the Weierstrass substitution. And what it does is it converts any like rational function in sine and cosine to just a rational function in t. See, the dx is what? Dx is 2 dt over 1 plus t squared, right? And this 2, well, that's 2. Cosine x is what? 1 minus t squared over 1 plus t squared. And then to clean it up, multiply everything by 1 plus t squared, top and bottom. So that gives me 2 dt over 2 times 1 plus t squared plus 1 minus t squared, which is what? This gives me
T squared cancel.
I think I get 3 plus 3 plus t squared. But this, of course, is 2 over 3 integral of dt over 1 plus t over root 3 squared, right? Which is an arctangent. I'm a little bit out of time here, so I'm just going to write it down. But I might be missing a normalization. I'll tell you in a second here. 2 over root 3. It works out to this. But, and then of course t is what was t? So this is a really neat substitution, right? Because it says any kind of fraction of sines and cosines that you face, you can convert it to a corresponding fraction of these sorts of things, and it always just works back to a rational function in t. Which rational functions can we integrate, guys? Was I like, you do partial fractions, but hey, there's this rational function out there we can't do partial fractions and solve it with? No, it's general. So this Weierstrass substitution, basically paired with the partial fractions technique, means that you can integrate any fraction of sines and cosines. This example is, well, it's his second example. It's got another idea which we haven't gotten to yet, so I didn't. We'll do improper integrals after test 1. So anyway, you guys can go. I'm sorry, I'm keeping you over time. Shut up. Here. We'll end a little bit early tomorrow.